there. I'm going to cover some moment of inertia derivations for students taking Physics C. I will derive the inertias for a rod pivoting around its center and end, a hoop, and a solid disk with uniform density, along with objects with non-uniform density and how to solve their center of mass. So let's get started. The first equation to memorize, since it won't be on your equation sheet, is mass is equal to the integral of your linear density times dx. Now let's define these terms in the sense of a rod. Now a rod can be drawn as this rectangular object that I have here, and it can be represented as a 2D object. That being said, we have the total mass of this entire rod as m, and we have the length of the rod going from 0 to L. So what this dx mean is that this portion, this instantaneous length, is going to be your d of x. All objects that have uniform density will have the following equation. Mass is equal to lambda L, where again mass is the total mass of your object, L is the total length of your object, so L minus 0, and lambda is your linear mass density. Now this can be rewritten as lambda is equal to m over L. So what this means is that with a given rod, this mass that's located in this dx will be constant for every dx. So what this means is that the mass that is collected in this instantaneous length will be constant throughout the entire length of the rod from 0 to L. So we can copy these over, and this dm will equal to this instantaneous mass. And this can be, like I said, done across the entire length of the rod. Now a good example of that is, let's say, an unsharp pencil or a meter stick. The mass at one end of your pencil or meter stick will be approximately the same at the other end. So we can write it as such that dm is constant for every dx from 0 to L. That means your mass is independent of position. Now let's keep these concepts in mind. The derivative of m is dm. The derivative of x is dx. Now don't worry about the differences between capital M and little m. If that confuses you, just know that capital M stands for the total mass of the rod, while dm with the little m represents the instantaneous mass at a given position. That being said, we usually want the format to be in d of m and d of x, because we have the equation that inertia is equal to the integral of r squared dm. So let's look at our original equation. M is equal to the integral of lambda dx. If we take the derivative of both sides, that means that we will cancel out this integral, make this mass as dm, we get lambda dx. That being said, we did have this moment of inertia equation where I is equal to the integral of r squared dm. Now, r could be length or radius, and sometimes you see in questions where they don't use the character r, but instead the character x. It does not matter how you define this. This is the same thing as saying that this is equal to r, which is equal to x. These just define the position of your rod. So now let's look at a problem of a rod with uniform density rotating about its end. So the pivot point, let's say, is located at position x is equal to 0. The first thing you want to do is write your moment of inertia equation and write the limits. So we have I is equal to the integral of x squared dm, and we're going to be integrating from the position of 0 to L. Now replace dm and simplify. So we have inertia is equal to integral of z. We have inertia is equal to the integral from 0 to L x squared dm, which is equal to the integral from 0 to L x squared. And we have dm equal to lambda dx. And now we also have that lambda, because it has a uniform mass, is equal to m over L. So we can rewrite this as the integral from 0 to L x squared m over L dx. And then I always like to put my constants in front, the variable that I'm taking my integral with respect to. Now we're going to integrate with respect to the limits. So we have the moment of inertia is equal to the integral from 0 to L m over L x squared dx, which is equal to m over L 1/3 x to the third with limits from 0 to L. Again, if these are difficult for you, I would suggest watching my math fundamentals video on how to take integrals. So that means we have 1/3 m over L, replacing the x with L to the third, minus 1/3 m over L, replacing the x with 0 to the third. This cancels out. We have 1/3 m over L to the third. As you can see, we can reduce this down further to 1/3 L squared. All right, so we have that derivation. Now let's look at how to derive the moment of inertia of a rod with uniform density, but it's now rotating about its center instead of its end. So the pivot point's located here. So first things first, we always write our moment of inertia equation with limits. So I is equal to the integral of x squared dm. Now the limits in this case is going to be from negative L over 2 to L over 2. So you see how the limits are different in these scenarios? Again, these are defined by their relation to the pivot point. Next, we're going to replace our dm and simplify. So we have I is equal to L over 2, negative L over 2, x squared dm, which is equal to x squared lambda dx. Again, because we have uniform density, lambda is equal to m over L. So this is going to equal to negative L over 2, L over 2, m over L x squared dx. Now we are going to integrate with respect to the limits. So we have moment of inertia. So taking the integral of this equation will give you m over L 1/3 x to the third with the limits from negative L over 2 to L over 2. So this will give you 1/3 m over L over 2, again replacing x with the top limit, minus 1/3 m over L negative L over 2 to the power of 3, again replacing the x with the lower limit and then negating it. So this will give us 1 over 24th ml squared for this portion. And because we have two negatives, and this is to the power of 3, we add 1/24th ml squared, and this will simplify to 1 over 12th ml squared. So you see how your pivot point determines your limits and therefore can change your moment of inertia equation. So even though these are the same rods with the same uniform density, where you define the pivot is very important in determining the moment of inertia. Now, it doesn't have to be a rod, it could be any sort of object. However, usually they won't ask you on the AP exam to do a derivation that isn't in the 2D plane. So let's, for example, have a linear mass density of m over L times x. So you see how this density is dependent on position. So very simply, we can draw it like this. And you can see as we increase the position, we will have an increase in density. So we can kind of draw it like this. We have some sort of mass. Let's say x is equal to 0 on this side, x is equal to L on this side. And as you see, the mass, the density is larger at x is equal to L than when x is equal to 0. So the first thing you want to do is replace lambda and derive dm. So the first thing you want to do is derive replace this lambda function and derive dm using that m is equal to the integral of lambda dx. So in this case, we're going to replace the lambda. So m over L x dx. And if we take the derivative of each side, that would cancel out the integral. That would give us dm is equal to m over L x dx. And then we can use the same operations as we did earlier. So first, we're going to write our moment of inertia equation with limits. So moment of inertia from 0 to L, x squared dm. And then we're going to replace this dm with what we derived here. So m over L x dx. And this is simplifying this, what we have here. And lastly, now we're going to take the integral with respect to the limits. So taking the integral of this will give us 1/4 m over L x to the fourth from 0 to L. So this will give us 1/4 m over L, replacing x with L to the fourth, minus 1/4 m over L, 0 to the fourth. This whole term cancels out. This will leave us 1/4 m, and these L's will cancel, so we have L to the third. So this would be then your moment of inertia of a rod with non-uniform density, given that the density equation is represented as such. Another common question you might be asked when it comes to non-uniform objects is defining the center of mass. From your equation sheet, you have the center of mass is equal to the sum of all your masses times their distance from their pivot, all over the sum of the masses. You can rewrite these summations as integrals because we have a non-uniform object. I would have this equation memorized since it's not going to be on your equation sheet. It's not a very common question to have on the Physics C exam, but it definitely could be a multiple choice or a portion of your free response. So for the integral of x dm, we know that we're going to be integrating for the entire length this object, so from 0 to L. We know that d is equal to lambda dx, which is also equal to, in this case, m over L x dx. So this simplifies of taking the integral from 0 to L, x m over L x dx, and we can simplify this further to m over L x squared dx. Now taking the integral of this will give us 1/3 m over L x to the third. When we plug in the limits, we'll get 1/3 ml squared. Now let's look at this portion at the bottom, this integral of dm. Again, from limits from 0 to L. dm can be replaced with this m over Lx dx. So taking the integral of this will give you 1/2 m over L x squared from 0 to L. And then this reduces down to 1/2 ml. So if we plug this into our equation, so we have x dm all over the integral of dm. This will give us 1/3 ml squared all over 1/2 ml. As you can see, the squared on this L and this L will cancel. 1/3 over 1/2 will give you 2/3. And we have the m's also cancel out. So we have 2/3 L. So that means that our center of mass for this object, given that the density is m over L times position, will be 2/3 L. And you should always do a sanity check, right? If the object was a uniform mass, we would always have the center of mass located center of the object, or in this case, the rod. Now, the fact that it's non-uniform, with the density being greater on one side, that means that the center of mass should be in the direction of where we have greater density. So in this case, we'll have it to the right of the halfway point. Now let's look at a hoop with uniform density. Again, uniform density is given this equation that m is equal to lambda L, or you can rewrite it as lambda is equal to m over L. So let's draw what this hoop is. Let's say that this hoop has some sort of radius of r. Let's make this point the 0-degree mark or the 360-degree mark, correct? So if we rotate an entire revolution, this point will be equal to 360 degrees. Now, a hoop is a circular object that has all of its mass located on the edge. Now, if we have a hoop with uniform density, let's look at this section. This arc or instantaneous length around its circumference, let's label this as dr, will have some sort of instantaneous mass. And if we have uniform density, that means with the same dr, let's say here, this mass will equal to the mass that we have located here. And this can be done all the way around its circumference. So we can write it as such that dm is constant for every dr from 0 degrees to 360 degrees, or that the mass is independent of angular position. Let's keep in mind that the derivative of mass is equal to dm. The derivative of angular position is d theta. As we mentioned before, this L is equal to the circumference. L will then equal to 2 pi r, correct? 2 pi is the same thing as 360 degrees. So if we want to look at only a certain portion of the circumference or an arc, we would replace this as an instantaneous theta, or some delta theta times r. And as we mentioned before, we usually want to put in the format of dm and dr because moment of inertia is equal to the integral of r squared dm. So m is equal to the integral of lambda dr. Taking the derivative of both sides will give us dm lambda dr. And as we said before, that dr is equal to d theta times r. So this will give us lambda r d theta. Okay, so as we did before, we're going to write our moment of inertia equation with limits. So I is equal to the integral of r squared dm, and we are doing this across the entire circle, completing one revolution, so going from a theta of 0 to 2 pi, or 360 degrees. Next, we're going to replace dm and simplify. So I is equal to 0 So I is from the integral of 0 to 2 pi r squared dm. Now we're replacing dm with this lambda r d theta. We get this. Now we also have lambda is equal to m over L. So we can simplify this to m over L r to the third d theta. And now we are going to complete the integration with respect to the limits. So moment of inertia from 0 to 2 pi over L r to the third d theta. As you can see, the variable that we want to take the integral with respect to is theta, not r. So that means that this entire portion of this integral is a constant. That being the case, this will equal to m over L r to the third theta from 0 to 2 pi. When we reduce this, we get r to the third m over L times 2 pi. Now let's keep in mind that our L is equal to 2 pi r, correct? Like what we have here. So your inertia is equal to r to the third times m over 2 pi r times 2 pi. And as you can see, this will cancel to make this r squared. These 2 pi's will cancel. And we'll get that the moment of inertia is equal to m r squared. All right. Now I do have the derivation for solid disk with uniform density as well. However, the likelihood of you being asked this on the Physics C exam is very rare. I have the derivation in the PDF notes located below this video. Even for a hoop with uniform density, the idea of deriving that is very, very unlikely. Now, it could be possible, hence why I did this derivation, but you're most likely going to encounter a problem with a rod and deriving the moment of inertia of a rod, if at all. And if you had non-uniform density, how would you deal with those types of problems? So that's all I have for derivations for moments of inertia. If you have any questions or concerns, please let me know. Thank you for watching.